I'm sorry to start this class too late because I have problem with my PC. But I don't want to waste time more, so let's start our class today. For your information, that the other class already have their quiz on Saturday, but because we still have the lecture to be continued, then I skip the first quiz on last Saturday for you. And I want to reschedule that quiz on Wednesday afternoon. So please prepare yourself and get enough exercise in order to be successful in the next quiz. Is it okay for you?
Yes, it's okay, sir.
Okay, thank you.
Excuse me, sir.
Yes.
Apa namanya? Kuisnya Rabu siang atau Rabu malam ya, sir?
Yeah. I mean Wednesday evening on 7:30 p.m.
Oke, makasih, sir.
Okay. So today's presence code, I will share it for you. Please wait a minute. So here is the presence code for today's meeting. And our first topic is how to design lozenge joint or diamond rivet joint. This is the first topic for today's meeting. Okay, so what so-called this lozenge joint or diamond rivet joint? It is a rivet joint that usually used in structural building. So, for example, the bridge, the girder, crane usually use this diamond rivet to assemble their component. Okay, so how this diamond rivet looks like? So if I draw here, suppose we have the plate here. This is the first plate, and next we have another plate on it. So this is an overlapped plate joint, and here we put the rivet. So this rivet has an arrangement So it has the arrangement that the number is increasing. The number is increasing as we proceed from the end of the join to the other end of join. So it's look like this. The circle represent the rivet. Okay, so I hope that you understand what I mean, that the diamond is represent this kind of shape. This is what diamond means. Okay, because the number of rivet is increasing. So this is for the first row, and this is for the second row, and this is the third row. The number is increasing 1, 2, and 3. Okay, and it is symmetrical. Left and right hand side always symmetrical. Okay, so that's what we call diamond rivet join, and you can find this in the bridge structure. So this is usually applied on the structural building. What we have discussed in the previous meeting, it's not on structural joint, but for mechanical part or mechanical building, such as boiler, such as high pressure tank. Okay. So the rivet method is kind of different. Okay. Can you understand this? So it has their own application. Okay, so the question is how to design this kind of joint. Okay, so how to design this kind of joint and determine the efficiency of the joint. Okay, so what is the first question? Usually, the plate is already defined or already determined, the thickness and the width and also the material is already determined. So if we see the front view of this joint, it seems like this. Then it has hole in this area, in this area. Okay. So let's go back to the topic. So the first question is how to determine the number. The first is the diameter. What is the diameter of the rivet? If the geometry of the plate are given, so what is the diameter of a rivet should be? Then next, the next question is how many rivet must be used? And how many rivet for each row in sequence? So for example, here we give an example that for the first row consists only single rivet. For the second row, we have 2 rivets. And in the third row, the third column, okay, we can say this row or column I think it's okay. So to make it similar with the textbook, so I will use row. Okay, so this is the first row, second row, and the third row. Here we have different number of refet. So how many refet is total, and how many refet for each row? Okay, so that's the main question in the design of this diamond refet joint. Okay, so let's take a look one by one and how to answer this question. Okay. So for the first question, what is the diameter of rivet should be used if we know the thickness of this plate. If the thickness of the plate usually it is in similar thickness, okay, has the same thickness. If the thickness are known, then the diameter should be the thickness, sorry, like this. Half the diameter must be 6 times with the square of the thickness of the plate. Okay, so T stand for the diameter and T for the plate thickness. Okay, so it has to be the diameter T and follow this equation, this formula. So how did we get this formula? It is from standard. So just follow the standard. They already doing many experiments to define this formula. Okay. So the next question is how many rivet in total in the joint? Okay. So for this question, we have to consider about the strength of the rivet and the strength of the plate. Both of them we have to consider. Okay, because the strength of the joint will be driven by the weakest part or the weakest component in that joint. So we don't know yet which one is the weakest, the plate or the rivet. Okay, so that's what we want to analyze for. Okay, so first we consider if this plate, so if this plate contain only single rivet, so if it has only single rivet here, then what is the strength of this joint? So how big the load capacity for this joint if we put only a single rivet here? So let's examine this. Okay, so here we have the plate which the thickness already reduced by the diameter of rivet. Okay, so initially it has the width of B or P. So for example, we have P here for the width, and here we have the diameter. So now the plate only has P minus D for the total effective weight. So the strength, the tensile strength for the plate is the tensile area multiplied by the strength of the material of the plate. Sorry, so it must be the load. So this is the sorry, I will change the notation so we will not confuse. So the width, the P stand for the width of the plate. So here we have, this is the load, the working load here. And here we have the area is the width minus by the diameter, okay, times the thickness of the plate and multiply by the strength of the material of the plate, the tensile strength. Okay, so here we will have the load capacity that can be resisted by the plate. Okay, so this is tensile load resistance. And if we only have a single rivet like this, then how about the shearing stress? So the shearing stress or the shearing load of the rivet is the shear area of the rivet multiplied by or times with the strength, the shear strength of the material. Okay. So here we have yield also. So the shear strength, because the body of the rivet is a cylinder, then this shear area must be function of the diameter of the rivet. So we will have the formula like this. Okay. So we so far we already discussed two kind of failure. First, the failure on the plate, okay, tearing failure, which crack the plate because of the tensile load. And next, the second failure mode is on the rivet, where the rivet can be cut by the shearing load. And next, both rivet and also the plate can be failure of the crushing load. So here we have the crushing load. So in the previous meeting, we already discussed that this crushing load is the area of crushing times with the compression strength, okay, or crushing strength or bearing strength of the material. Okay, so where is the crushing area? The crushing area is the projected area of the rivet. So here we have, this is the diameter, and this diameter has the thickness. So Here we have the area, the crossing area. That must be the diameter times the thickness. So here we have the strength, the crossing strength capacity. Okay. Okay, so come back to the main question. So must be used in this joint. So check the value. Then the number of the rivet can be determined by the lowest or the minimum compare with sorry. Okay. So now to calculate the number of rivet, we just take the ratio between the tensile strength or tensile load resistance, which is usually the largest one, because we only reduce the area, the tensile area of the plate with a single rivet only. So this strength or this load resistance is closest to the ideal joint or the plate without joint, because it consists only one rivet hole on the plate. So that's why we put this tensile load or tensile strength here for the plate. And for the divider, we choose the minimum between the shear strength and the crushing strength. Okay, so using this formula, then we can define how many rivet must be used. So for example, we have the weakest part is the shearing resistance. So we will choose like this. Okay, so in this formula, we can see that in order to have an equal strength between tensile and shearing on the rivet, we have to put some rivet. We have to put some number of rivet here, which represent by n. So in this case, we will have the balance between the tensile failure and the shear failure. So if this joint break up, then uh, it can be resisted by both of them. Okay, so it has higher strength capacity. It has higher load capacity because they are in balance between tensile on the plate and shear on the rivet. So that's how we determine the number of rivet in total. Okay, and please be careful that when calculating this shear load, please check the type of the joint. Here we only use a single shear area because it is an overlap joint. So it has only a single shear area for one rivet, for a single rivet. But if we use double butt strap butt joint like this, if we have this kind of geometry, and here we put the rivet, then here we have two, theoretically have two shear area here and here. Then for this kind of geometry of joint, you have to put these two shear area for a single rivet. Okay, so please be careful in calculating the shear area. So far, is there any question about this problem?
Not yet, sir.
Not yet. Okay, so let's continue. Okay, so now the next question is how the arrangement of the rivet. How many rivet for each row? Okay, so how many rivet for each row? Okay, so for this question, we have several possibilities. So we can put, if we have 6 rivet, for example, if we have 6 rivet, then we have several possibility. So we can put 6 to be like this in this arrangement, or we have this kind of something like this. So how to determine the number of rivet for each row? Okay, so please wait a minute. I will give you a problem first to determine the number of rivet. You can work in the group for this. So I will give you a problem. Suppose you have this double strap butt joint. and the geometry of the plate is given. If the width of this plate is 200 millimeters and the thickness of the plate is 12.5 millimeters, and if the tensile strength of the plate is 80 megapascal, and the shear strength of the rivet is 65, and the crushing strength or compressive strength of the plate and the rivet is 160. So if I want to design the double strap butt joint like this, then the question is, what is the diameter of rivet? And how many rivet in total? So please work on this example and let's discuss the result. Okay, so you have about 10 minutes to work on this question. Then let's discuss your result. Okay, finish? Hello? Is it finished?
Not yet, sir.
Not yet. Have you finished?
Sir, excuse me, sir.
Okay, so is there anybody who want to show his or her uh, result? Anybody want to try this to solve the problem? How if I ask Dirga?
Yes,
Dirga,
sir.
please
Yes, sir.
show your calculation.
Can I write it? Can I annotate on the screen or have I
Okay, I will give you permission to share
wait,
to
sir.
write on
I
the
will-
on the whiteboard. So please
Oh.
wait a minute. Okay, so you can write annotation on this whiteboard.
The A part, sir.
Pardon?
I still cannot annotate your screen.
Oh, okay. So how about Kafka? Can you show to us?
Yes, sir.
Yes, please share with us your result, Kafka.
Wait, sir. Let me take a picture first.
Mhm. Okay, Kafka, are you there?
Yes, sir.
Uh-huh.
Yes. Can you see it now, sir? Okay. So for the first question, the diameter of rivet, as you previously said, the formula is D equals to 6 times the root of the thickness. So here it's 6 times the root of 12.5, which equals to 15 times the root 2 millimeter. Then for the how many rivet, so first I calculate the load for the tensile. The formula is the width minus the diameter times the thickness and times the tensile strength. As you can see here, this is the numbers, and the result is this. And then for the shear load, the formula is 2 because it's but joint rivet, and then 2 times P per 4 D squared times the shear strength of the material, and this is the number. And then the compressing load, the formula is the diameter times the thickness, and then the compression strength, and this is the number. And since the PC is lower than the PS, and for the formula to find the number of rivets, I use the PC,
Mhm.
and then I divide the PT with the PC, and I get 4.2.
Hmm. Okay, so how many rivets that should be used for your join, Kafka?
4.2, sir.
So how you make 4.2 for the rivet? It should be on integer. So 4 or 5. Which one should be used? 4 rivet enough, or we have to add more one?
I think it's 4, sir.
4?
Yes.
Okay. So now if you have 4 rivet for the join, then how we arrange, okay, how we arrange uh, the rivet in the join. That's the next question. Okay, so Kafka, you already done a very great calculation, and maybe we have a different result because of the number, but I think it is not a problem. So the important is the concept here. So now you are able to find, to determine the number of the rivet required in the joint. And next, okay, let I share my whiteboard with you.
Should I stop share, sir?
Okay, please stop it. Stop yours and give me the chance to present my whiteboard. Okay, have you seen it? My whiteboard?
Yes, sir.
Yes, sir.
Okay, so let's go to the next step. So Kafka already showed to us how to find the number of rivet. So he compared taking the ratio of the tensile strength or tensile load with single rivet to the minimum between the crush and shearing load. So he found that the minimum is the crushing load and found the number of rivets is like this. If Kafka choose 4 rivet only, then what kind of failure that will be appear on this joint? So because he choose 4 rivet only instead of in this joint. So the failure in the crushing mode. Okay, so the failure will be in crushing mode where the rivet is crushed or deformed because of the bearing load or crushing load. So how if we choose 5 instead of 4? Is it okay for us? So if we choose 5 pieces of rivet, then here we have higher crushing resistance. So the failure will be on the plate, the tearing failure. So the plate will be cracked because it has lower resistance than the crushing resistance. Okay, but it already in 5 times PC, so it will be higher. Then it is okay to use 5 rivet instead of 4 because when the load reach 5 times the crushing load, then the plate will start to collapse, will start to crack. Okay, but it happened in higher load, so it is okay. So I think choose 5 pieces of rivet is better, can increase the strength of this joint. Okay, so usually in the design, if we found that if we found the decimal number of rivet, then we take how to say, we choose the bigger integer for this value. So instead of 4, we will choose 5 in our design. Okay, so it should be like this. If you choose 4, then you will have lower load resistance. Okay, so here we decide to choose 5 pieces of rivet. But how it will arrange on the plate? So here we have if we use 5 rivet, means we have 5 rivet for the left side and 5 rivet for the right side. So we can arrange like this. Sorry. So for the left side, we have 5 like this. And also for the right side, we also have 5. Okay, so because 5 rivet only, so the arrangement, if following this diamond pattern, then we will have 1, 2, and 2. We cannot give more rivet in this row because we only have 5 rivet. Okay, but if we have 6 here or 7 here, then we have to increase the number for the last row. Okay, so why we use less rivet for the first row and then increasing later? Because this pattern give us the uniform strength distribution for each row. So next we will find the reason. Okay, we will find the reason soon.
Excuse me, sir. I want to ask you something.
Yes, please.
So the calculation for the number of rivet is just for one side, sir.
For this kind of geometry, yes, for double strap butt joint. But for the single lap, for this kind of joint, then the total rivet is the total number in this overlap. Okay, so if you found 5 here, then means the total number of 5 for this whole joint. So it should be like this. 1. Okay. But for this kind of joint, 5 rivet stand for the left side and the right side. Why? Because we can remove this, and only this plate we have. Then we can put the load here. For example, P, T, or P, and here we have. Okay, so five rivet will be on the left side here in this overlap joint. So 5 is here. Okay, and for the right side also have similar situation. Okay, if we remove this left plate and pull the right plate, then it has also the same load state like this. So that's good question from Sultan. That, this geometry has an effect on the number of the rivet, the total rivet. Okay, so what we calculate is the total number of rivet on the overlap area. Okay, so for single lap like this, we just have a single overlap. So 5 rivet are put on this overlap area. But for the double strap butt joint like this, we have 2 overlap area. This is the first, and this is the first, and this is the second. Okay, and for each overlap area, we have to put 5 rivet. Okay, that's the answer, Sultan.
Okay, sir. Thank you very much, sir.
Is it clear, Sultan? Or you still have questions about this?
It's clear now, sir, for me. Thank you very much.
Okay, sorry, I have a problem with my headset, so I cannot hear you clearly. Okay, so let's continue about this if there is no other question. Okay, so if we have the arrangement of rivet like this, then how to calculate or how to determine the efficiency? How to calculate the strength of this joint? Okay, so first I will remove this. Okay. So let's let's analyze the strength for each row. So this is the first row, and this is the second row, and this is the third row. So what is the strength for each row? And by taking the lowest strength in this row, then we can examine or determine the efficiency of the joint. Okay, so first is for the first row. Okay, for the first row, for the first row, we will calculate the tensile strength, the tensile load, maximum tensile load that can be held or resist by the first row. So here we have only one rivet there. So it will be like this. Okay. So it will be 200 minus the diameter. Okay, the diameter of rivet. So in my calculation, the rivet diameter is 21.2 millimeters. And the thickness is in millimeters. And the strength, tensile strength is 80 millimeters. So here we have the tensile strength for the first row is about this, or kilonewton. This is the load capacity that can be resisted by the first row. Okay. And for the second row, here we have, this is for the first and this is for second. We have two rivet in second row. So it should be like this. Okay, so this is the thickness. This is the addition with the row strength. Okay, so why this can happen? Why we have to put the strength of the first row to the second row? Yes, because the load come to the first row first. So this is the closest row to the load here. Then if we analyze the second row, then the remaining load is much lower here. So this load is resisted by the first rivet in the first row. Then the remaining load is resisted by the second row. And the remaining load later also resisted by the third row. Okay, so that's how we calculate the strength for each row. So please don't forget about this. So here for the second row, I'm sorry, I have a mistake here. Not the. This is not tearing, but shearing. Okay. Shearing. Okay. So the load already resist by the shearing load of the first row, rivet on the first row, and so the next row, which is the second row, will have the addition of the strength from the first row. Okay, so here we have kilonewton. Okay. And how about the third row? We have 2 rivet also. But please don't forget to add the resistance, the shearing resistance of the total rivet in front of the third row. Okay. So here we have in front of the third row, we have 1, 2, and 3 rivets. So here we have 3 times the shearing load, okay, for 3 rivets. Then here we have the shearing load is about this, okay. So from this calculation, we can see that the weakest part of this joint is in the first row, okay, in the first row. This is the minimum. And how about the shearing resistance for all the rivet? The shearing resistance for all the rivet is, we have 5 rivet, and this is the shearing resistance for 1 rivet only. So here we have about and for the crushing for all rivet, here we have sorry, we have 5 rivet also, and this is crushing resistance. Sorry, for this calculation, we have to put the minimum between the crushing and shearing. Which one is the minimum? So based on Kafka calculation, the crushing resistance is minimum. So here we have to put the crushing resistance, not the shearing resistance. Okay, so here we have 3 crushing resistance. Okay, so in our calculation, we have kilonewton. Okay, so we have 206 for shearing resistance and 215 kilonewton for crushing resistance. And here we have the tensile resistance for each row, and the minimum is 178.5 kilonewton. So what is the efficiency of this joint? So which one determine the strength of this joint? Okay, so of course, the failure will be occur at this part first, because it has the minimum or the lowest resistance here. So the efficiency is determined by this. Compare with the ideal joint or plate without joint, the strength of plate without joint. So it must be like this. And here we have the efficiency is 89.25%, obtaining from this ratio. Okay. So what we have demonstrated here is how to analyze the strength for each row. Okay. So why we calculate only the tensile strength? Why we skip to calculate the shear strength and crushing strength for each row? Why we only calculate this? We also have different shear and crush resistance for each row. Yes, of course. Here we assume that we choose 5 pieces of rivet, right? So here we have 5 pieces of rivet because actually the rivet should be 4.2, and instead of this we choose 5. So we make this term larger. So the shearing strength is larger than the tensile strength because we choose 5 rivet, higher than it should be. Okay. The required is only 4.2, but we use 5. So the capacity for shear load and crushing load is larger than the tensile strength. So this is become the weak point of the joint. So this tensile strength for the plate and assume that for the shear and crushing strength of the so that's how we analyze the stress and strength distribution on each row. Okay, so is there any question about this?
Excuse me, sir. I want to clarify something.
Yes, Sultan.
Also, when we put the addition from the second row is we use PC, right, sir? It depends on the lowest value from PC or PS, kan, sir?
Yes, that's right.
Okay. Thank you very much, sir. It's clear
You're
enough for me.
Okay, you're welcome. Okay, no question? Other question? No? Okay, so next is to determine the thickness of butt straps for this kind of joint. So this butt strap, this is the strap, the additional plate that keep the main plate stay still, or to keep this main plate in joint. So we need this butt strap plate. This is also plate. So what is the thickness for this strap plate? So the thickness is, it should be 75% of the main plate thickness. So the strap thickness must be 75% of the main thickness, the main plate thickness. So that's how we calculate the thickness of this strap joint. And then next is, please consider the pitch of rivet Okay, so the pitch of rivet that must be used is 3 times of the diameter plus 5. So between this row and this row, the pitch distance is 3 times the diameter plus 5 millimeters. This is came from the standard. If we use the shortest distance, I mean shorter distance than this, or between the rivet is too close, then there is a tearing failure will occur between this rivet, something like this. Okay, this is too close. Then there is the tearing failure. And how about the marginal pitch? So the distance between the diameter with the edge of the plate. So the distance, this is also pitch. Okay, this is the pitch, also the 3 times the diameter 5, and this is the marginal. Should be keep. Okay. Okay, like this. So we have to consider also this distance from the edge and distance between the rivet in order to avoid tearing failure of the plate. Okay. So this is the first example in designing the diamond rivet joint. Okay, let's take a break about 10 minutes. Okay, I want to drink something, so please give me 10 minutes. Okay, let's start again our discussion. I will clear this whiteboard and let's have another example, okay, to make it clearer for us how to design this rivet joint. So, for example, here we have to design a single lap joint, okay, with the plate of 200 millimeters of width with 10 millimeter of thickness. Okay, so let's write what we know here. So the design purpose is lap joint, single lap joint. Okay, so this single lap joint should be like this. Okay, and this plate has the thickness and the width described. Okay, so the thickness is 10 millimeters and the width is 200 millimeter. Okay, and the diameter of rivet that we use is 24 millimeter. And now we have the data from the strength of the material. So the allowable tension and compression stress of the plate material is, so for the plate material have tensile 112 and compression strength is 200. And the shear stress of the rivet, is 84 megapascal. Okay, so how to design the rivet joint for this single lap joint? Okay, so first let's because we already know the diameter of the rivet, we don't need to calculate it again. So let's go directly to the number of rivet in total. Okay, so the total number of rivet will be determined by the tensile strength of plate with single rivet. So it will be like this. This is the strength, tensile strength of the plate. So B we have 200 and D we have the diameter is 24 and the thickness is 10 millimeters and the strength, tensile strength is 112 megapascal. So here we will have for single rivet the tensile strength or the tensile capacity is okay. So 195.44 kilonewton. And How about the shearing load capacity for single lap joint? Here we have the shear area. Because we use single lap joint, so only single shear area we have here. That is P over 4, the diameter in square, times the shearing strength of the rivet material. And here we have sorry. Okay, 42.9 kilonewton. And how about the crushing area? So it should be like this times the compression strength of the plate. And here we have for single rivet 51 kilonewton. So the number of rivet that should be used is determined by the tensile resistance, the maximum allowable tensile resistance compared with the minimum between crushing and shearing stress. So that is the shearing stress here we have. So we choose this. And the calculation we have 4.56 rivet. So we choose 5 pieces of rivet. Okay, because we choose 5 pieces of rivet, so the shearing capacity will be higher than the tensile resistance. Okay, so next in calculating the efficiency or the strength of each row, we will calculate only the tensile resistance only. Okay, so we have 5 pieces here. So how to arrange these 5 pieces of rivet? Okay, so because we have only single lap joint here, that means only one overlap here. Then we put the rivet 1 at the end of joint. Then we have 3 remaining. We put it in the middle. So this is the first row, this is the second row, and this is the third row. Okay. It is symmetrical. Okay, so because the plate also similar, the thickness, the material, the geometry is the same. So we put this, how to say, a symmetrical arrangement of the rivet. Okay, so now we have this arrangement. So we need to calculate the strength of each row. So the first row, for the first row, we have only single rivet here. So the maximum allowable tensile strength for the first row is determined by this. And here we have it similar like this one. And for the second row, we have 2 rivet but please don't forget to add, we have one rivet in front of the second row. So we have one rivet in front of the second row. So we have to put the strength, the shearing strength here. This is the weakest one. The shearing strength for the for one rivet. Okay.
Excuse me, sir.
Yes.
Isn't that 3 rivets in the second row, sir?
Yeah, but what I said is we have to add the shearing strength of the rivet in front of the second row.
I mean for the diameter, sir.
Oh, I see. Okay, okay. Thank you, thank you. Okay, thank you for reminding me. Yes, you are right. We have 3 rivet here. Okay, so and here we have to put this one. Okay. Okay, and then it should be just wait a minute. $181. Okay. Sorry. And for the third row, you can make a calculation, but because it is symmetrical, then it should be similar with this one. Okay, so for the third, yeah, it is similar. It is in symmetry because symmetrical arrangement, then it will have symmetrical strength also. So it should be kilonewton. Okay. So this is the allowable resistance load for each row on this joint. And we found that in this calculation, we found that the second row is the weakest part of this joint because it can only resist maximum 181 kilonewton. Okay, so we will use this to calculate the efficiency of the joint. So the efficiency of the joint should be the weakest part of this one, the minimum PT, PT, PC, and PS. Oh, wait, we have to calculate the total for PS is we have 5 rivet times, this is for 5, and for compression for 5 rivet we also, okay, here we have about 200, okay, 210 kilonewton, and for this one is kilonewton. Okay, so this is the minimum. This is the minimum between 3 of them. Compare with the plate without joint. The strength, the tensile strength of the plate without joint. So it should be the width times by thickness times by the tensile strength of the plate. And here we have this. This is kilonewton, and this is also kilonewton. So here we have the efficiency of this joint is about 80.9%. Okay, so this is the efficiency of our joint. Okay, so I hope that you recognize the difference between the design on a single lap joint and the design of the double strap butt joint. Okay, Sultan and other friend already mentioned, already identify the difference between these two designs. So to emphasize, so for the single lap joint, the total rivet will be put on this single overlap area, but for double strap butt joint, the total number of rivet only represent the number of rivet on the left side or the right side only. Okay, only half of them. So if you use the double strap butt joint, you will need 2 times the total number of rivet found in the calculation. So in the previous example, we calculate that we need to use 5 rivet, but in the joint we put 10 rivets, 5 on the left side and 5 on the right side. So that's how the lap joint and double strap butt joint differ. Is it clear for you?
It's clear.
Okay. How about others? I don't hear.
Can I ask a question?
Oh, yes, Farhan. Yes, please.
In the second row, I still don't understand why do we sum it with the stress of shear? Why don't we use the crushing stress?
Okay. So,
yes, that part.
From this calculation, we found that the weakest part, or the weakest part is the shearing failure, not the crushing failure. I mean, the shearing load is smaller than the crushing load. So this will be determine the strength of the joint, not this one. Okay. So that's why we choose the shearing strength, not the crushing strength. We always choose the minimum one between these two.
So does that mean we use the crushing load if it is the lower?
Yes. As you found in the previous example, right?
Oh yeah. Thank you, sir.
Yeah, you're welcome. You're welcome. Okay, that's a good question. If you don't have any other question about this kind of joint, then we will move to the next example, which demonstrate to us how to design the eccentric, the rivet joint with eccentric load. Okay, so here in this example, in both example, we have that the load work in this joint is in line. Okay, so it is always pass through the symmetrical line of the plate, or in other words, it always work in line with the center of joint, the center geometry of the joint that is in the symmetrical line. So this kind of load doesn't initiate moment in the joint. Okay, so there is no torsional or moment work in the joint because this load is is work in the single line, in the symmetrical line. Okay, so for the next example, we will have the eccentric loaded riveted joint. And for the example here, we have cassette. Okay, let me draw for you. Okay, here we have okay, so we have two plates and it is joined by the rivet, but not in uh, not in a axial line, but it is perpendicular. Okay, so for the first plate, it is vertical, and for the second plate, it is in horizontal. So it is perpendicular. And here we have the rivet put here to maintain this joint. Okay. Then there is an external load applied outside the joint. So that's why we call this the eccentric joint, because this load, this force doesn't apply in the center of the joint. Okay. It has an eccentricity. So if we give the name of the rivet one here, this is the first rivet and this is the second rivet. And this is the third, this is the fourth. Then it has the center of the joint. Where is the center of the joint? We have to find it first. Okay, we have to find it first. And we can use the geometry calculation for this if we consider that this is the x-axis and here we have y-axis. Then here we have, we can measure the position of each rivet. Okay, so this is the coordinate of each rivet. This is x1 and x4 will be the same, and here from 0, which is x2 and x3 is the same. And also for y direction. Okay, so here we have y 3 and 4, and this is y1 and y2. Okay, so where is the center of joint? Yes, geometrically we can find that it is lay on this diagonal. So this is the cross point between this diagonal line. But for algebraically, we can calculate that the x bar. So this is the x bar should be the total rivet in this x1. So we have 2 rivet in x1 that is the rivet number 1 and rivet number 2 plus 2 rivet also in the second line. So here we have divided by the total number of the rivet. Okay, so here we have x bar, and also for y bar, we have 2 rivet also for this and 2 rivet in vertical. Okay, so using this equation, we can find the location of the center of joint, that is x bar and y bar. Okay, so while we calculate the center of this joint is to measure the eccentricity. Okay, so this is the eccentricity. Because we have eccentricity here, this load can create moments or torsion load on this joint. So it will turn this joint in clockwise direction because we have moment here. Okay, the eccentric moment is okay. So that's the geometry of the eccentric joint. So let's analyze what kind of load that resists by each rivet. Okay, so let's draw the free body diagram here. We have 4 rivet here. Okay, and we have the center located here. And we have the load is far from this point G. So let's draw the force acting on each rivet because of the external load P. Okay, so each rivet will hold the plate in order to not go down. Okay, so it will hold the plate in this direction to resist or to keep the external load in zero. Okay, so it should be P of 4. So we call this direct shear because it comes from the vertical load directly. So we call this direct shear load. And we can assume that this load is divided by the number of the rivet. Okay, divided by the number of the rivet. Then this external load also create moments which turn the joint into clockwise direction. So in order to be in static condition, there must be exist load that can resist that rotation. Okay, so sorry, I will choose another color for this. Blue, I think it's okay. And the direction is always in perpendicular with the distance with the point at the center of gravity. So it will be like this. Okay. And what is the magnitude for each rivet? What is the magnitude for this one? That's what we want to calculate. Okay. So if we give the name of each rivet like this, then we can define this is F1, this is F2, F3, and F4. And here we have the distance, the length, L1, L2, L3, L4. And so the turning moment created by the external load will be balanced by this reaction force. So here we have F1 times the distance from the center of gravity, and F2 also F3 and F4. Okay, must be unequal. So here we have if we have F1, L1 and L2 and L3 and L4 are equal, then we have F1 plus F2, F3 and F4 equal. It's only if okay, so we have here. So then we can have the total F, sigma F, is equal to P, the eccentricity, and L. Okay, so like this. If F is equal also, then here we have for F, then we can calculate F1, F2 until F4 is something like this. Okay, so F1 and this direct shear load apply on the same plane. Okay, applied on the same plane. So that's why we can find the resultant of this force. Okay. So this is the resultant of the shear force in the first rivet. Okay, so this is R1 and this is R2 and this is R3. Sorry, this is R4. Okay, so by observing this parallelogram of force, we know that the critical part means that the most bigger resultant can be found in here and here. Okay, so here we have to calculate the resultant at this rivet. It will be the same with this one. Okay, so now we can find the resultant using parallelogram of force. Okay, so here we have, this is alpha, P over 4 square plus F square plus 2 P over 4 F cos alpha. Okay, so this is the total load applied on the first rivet. Okay, this is the total load that resists by the first rivet. So this load will create the shearing failure. Okay, will create the shearing failure and crushing failure on the rivet. Okay, so we want to calculate both of them. Okay. So because this rivet has only single shear area, then the shearing load is R1, the shearing area of the rivet. Okay, so this the R1 divided by P of 4, the diameter of the rivet. Okay, and about the crushing, it's also R1 divided by the crushing resistance. So it should be, so R1, the diameter and the thickness of the plate. So this is the working shearing load, and this is the shearing stress. Sorry, this is actual work shearing load, shearing stress. And this is actual work of crushing stress. Okay, so we should compare this. This is for stress. I think it is better to use this one. Okay. So this is the stress, and this is the, okay, like this. Then we can compare this work stress, this shearing and compressing stress with the properties of the rivet material. Okay, so if the strength, if the working shearing stress on the rivet is still less than the allowable shear strength of the rivet, then it is safe. Okay, and also for the crushing resistance, if it's still lower than the compressive strength, then it is safe. Okay. Okay, let we resume. Let we make it shorter. Okay, let's resume this. For the eccentric joint, first we have to found the geometry, the center of geometry. I mean, okay. Then next, calculate the eccentricity that measured from the load to the center of joint. Okay, so please find this one. Then draw the free body diagram and identify and describe all the working forces. So for example, in this problem, we have direct shearing load and shearing load that induced by the turning moment. Okay, we have P over 4 and F, which is induced by the moment here. Then using parallelogram, you can check which part is the critical one, which rivet that hold or resist the maximum load, and take this rivet in the analysis. Okay, so for example here, we have the first and the third rivet resist the highest load. Okay, so from this resultant, then calculate the working shearing stress and also calculate the working crushing stress. Then compare with the strength of the material in order to determine, to judge whether this design is safe or not. Okay, so that's how we design the eccentric joint. Is there any question here?
Sir, I want to.
You first, Tim.
Okay, thank you, Sultan. I want to ask if I want to search the tensile stress of the plate. Oh, sir.
Oh, how to calculate the tensile stress of the plate? Is that what you mean?
Yes, sir.
Yeah. Okay. So it depends on the direction of the load, Atin. So for example, here we take the first rivet as the critical one. So we know that the resultant of forces is directed to here. Then this is our plate here. So the most possible fracture on the plate will be in this direction. Okay? Will be in this direction. So here we have to apply the calculation for the tearing plate in this cross section also. Okay, so here we have R1 and here we have R3, which is equal but in opposite direction. Then it will create cracks on this plate. So just the tensile strength work in this plate is R1 divided by the tensile area of this plate, which is the diagonal of this plate. Okay, so for example, this diagonal have the length of B. So here we have B minus 2 diameter of the rivet, and it has the thickness also. Okay, so this is the working tensile stress on the plate. So you have to compare this with the tensile strength of the plate in order to be safe. That's how we calculate this, Adin.
Okay, thank you, sir.
Yeah.
So is the plane of the tearing perpendicular of the resultant, or it is just diagonal of the plate? So
Yes,
diagonal of the plate.
Perpendicular with the load. Yes, you are
I
correct.
see.
Perpendicular with the load.
Okay, sir. Thank you.
You're welcome. But I want to remind you that from the experience, it is no need to calculate this tensile stress, because it always has a higher value compared with the shearing and crushing stress. Okay, so the dominant failure will be shearing on the rivet or crushing on the rivet for the eccentric joint. So that's why in the textbook, we cannot find, or we don't find the analysis for this tensile stress for the plate. Okay, because it is not the critical one. The most critical part is the shearing on the rivet or crushing on the rivet and plate. I mean, can you understand this?
Yes, sir. Thank you.
Okay. You're welcome. So next question, if any.
Excuse me, sir. I want to ask something.
Yes, Sultan.
It's about the direct shear, sir. So
Direct.
the direct shear is always a parallel with external load, right, sir?
Yes, always.
So when the external load is made an angle with the horizontal line, so the direct shear has an angle too.
Also,
right?
yes, must be. So the direction of the direct shear must be opposed the direction of the external load. Okay, that's good question, Sultan.
Okay. Thank
Always
you, sir. Thank you very
opposite.
much.
You're welcome. Always opposite. Okay, and please be careful what we draw here. What we draw on the free body diagram are the reaction force, not the acting force. Okay, so that's why the direction of this direct shear is opposed the direction of the external load. And the direction of this force is opposed the direction of the turning moment. The turning moment should be in this direction. Okay? But this force opposed this moment. It turned to the counterclockwise direction. So what we draw here, I want to emphasize, what we draw here is the reaction force. Okay? The reaction force. So if we follow that procedure, then we can have this equation. Okay? Is it clear for you?
It's clear enough, sir, for me. Thank you very much.
Okay. So far, what we show here, what we has demonstrated here, is just the concept, but we need to do the calculation. Okay, except for exercise, we have to do the calculation, but we don't have enough time, so I will give you an assignment. Okay. You have to submit this assignment by tomorrow. Okay? And you will have the quiz on Wednesday. So after you submit your assignment, then I will release the answer for that problem so that you can check by yourself whether your answer correct or not. Okay? So in that way, I hope that you have enough understanding and enough exercise to do the quiz on Wednesday. Is it okay for you?
It's okay, sir.
Okay, sir.
Thank you. So I will release the problem soon after this class finish. And you have 24 hours to submit your answer and to obtain the answer from me. Okay, so I hope that you will be success in quiz on Wednesday, and see you in the next meeting next week, and we will discuss about weld joint. Rivet joint already finished by this eccentric load. Then we have to move to the new topic, that is the weld joint. Okay, so see you next week. Assalamualaikum.
Waalaikumsalam.
Waalaikumsalam.